What's up, everybody? Welcome back to Mathlete's Corner. In this video, we're going to continue with our 2025 ARML series, and we're looking at problems 5 and 6. So let's get right into it. So we're starting off with a nice geometry problem, so I encourage you to pause the video, read the problem, and try it yourself, and then come back for the solution. So now that you've tried the problem, we can go ahead and label an 8 there, an 8 there. And now I think a natural step to make is to assign a variable. So we can go ahead and assign this here, xg, to a variable x. And we're also given xg is equal to zi and dh. So we can go ahead and label those as x as well. Now we can also notice that we have so many similar triangles in this diagram. So for example, these two triangles here are very clearly similar. And in fact, since we know that those two side lengths are equal to x and x, we can actually say that those two triangles are congruent. Because we know that this total length ID is also x, since this here is a rectangle, we can say that each of these side lengths is x over 2. And at this point, we see our ratio for our similar triangles. And we see that our legs are in the ratio 1 to 2. Now that we have that information, we can get rid of the variables, and we can say this is 4, this is 16, 4, 4, and since xy has a total length of 12, we can say that xz has a length of 24. And we can find quickly that fd has a total length of 28, so de has a length of 14. At this point, we have to remember we're looking for the larger area of DEF and XYZ. So when we do that, we see that our two areas come out to 12 times 24 over 2 and 14 times 28 over 2. And clearly, the 14 times 28 over 2 is larger, and it comes out to 196. And that's our answer. On to the next problem. Problem 6 reads, compute the least positive multiple of 7, expressed as a base 10 number, that has exactly 7 ones in its binary representation. So we're looking at the mod 7 of a binary number. So let's go ahead and consider each place value separately and try to convert it to mod 7. So obviously our 1's place is just 1 mod 7, our 2's place is 2 mod 7, 4's place is 4 mod 7, and then we start to see that our 8's place is again 1 mod 7, our 16's place is 2 mod 7, and we start to see 1, 2, 4, 1, 2, 4 as a cycle repeating over and over. At this point, if we take our 7 smallest powers of 2 and add them up, we see that we get a sum that is 1 mod 7. So unfortunately, that doesn't work. So we move on to our next place value. So we get a 2. But now we have 8 numbers that add up to 3 mod 7. And we want to get rid of one of them because we only want to keep 7. So we have to get rid of a 3 mod 7. But we don't have any 3 mod 7s. So again, we need to move on to the next place value. And that would be 4. At this point, all of our numbers add up to 0 mod 7. So we need to get rid of 2 numbers that add up to 0 mod 7. And again, we don't have any such pairs of numbers. So for the last time, we move on to our next place value. And now the total sum comes out to 1 mod 7. And we need 3 numbers that add to 1 mod 7. And we can quickly notice that 4, 2, and 2 add up to 8, which is 1 mod 7. So if we just get rid of those, we're left with 7 numbers, and I encourage you to double check that these 7 numbers do indeed add up to 0 mod 7. So when we add up our powers of 2, we get 2 to the 9th plus 2 to the 6th plus 2 to the 5th plus 2 cubed plus 2 squared plus 2 to the 1 plus 2 to the 0. And that ultimately adds up to 623. And that's our answer. That's all for this video. Thank you for watching. Don't forget to hit that like and subscribe button, and we'll see you next week here at Mathley's Corner.